change slides here. The mouse, I don't see any, the mouse doesn't seem to work.
It was 25 minutes, not 20.
Okay, I can change slides with this, but the mouse itself. Okay, so. Okay. Okay, it'll be tough to follow up that excellent lecture. I took the liberty of using the background slide to show some of my wife's art in the background. It looks a little bit like a whole body CT scan. So anyway, I'm talking about pre-procedural CT assessment of aortic annulus dimensions, and actually dealt mainly with prediction of optimal C-arm implant angle before TAVI, which can reduce complications related to incorrect prosthesis sizing and positioning. It can also reduce the use of contrast and radiation exposure, and it's known that consequences of incorrect sizing or implantation sites are associated with poor long-term outcome and include annular rupture or aortic regurgitation. On the other hand, performing these CT measurements requires significant expertise and can be time-consuming. So we aim to evaluate a novel automatic software platform by comparing results of automatic, semi-automatic, and manual predictions of the optimal implant angle of the valve by cardiac CT. We aim to compare results to the actual deployment angle recorded at the end of the TAVI procedure, to compare Edwards and Medtronic core valve devices. And we also looked at the annular dimensions, but I will not do that in this presentation because of time limitations. We looked at pre-procedural CT scans that were retrospectively performed in 61 patients, half of each valve type, and we performed automatic, semi-automatic, and manual measurements. We used dedicated CT workstation, Philips IntelliSpace Portal version 6, and this platform uses a model-based segmentation of the heart and aortic roots. It works something like this. One loads the data and obtains automatic identification of the annular plane, which is defined as the nadirs of the three aortic cusps. We also get other information at the same time. At this stage, we can either take the automatic results or we can adjust it, being the semi-automatic method. At this stage, we have the opportunity of looking at the contour of the aortic annulus and changing the measurements if it's semi-automatic. But in this study, we looked at the angles, and this is actually represented by a line of perpendicularity around the aortic annulus, which is an infinite number of angles, potential angles, which can be used for the C-arm. Obviously, in actual fact, we choose only one or two angles, but for the purpose, at this stage of the research, we actually recorded the whole line of perpendicularity. How is actually the deployment performed? The deployment angle, it's done slightly differently for each valve type. The deployment angle was determined based on aortic fluoroscopy with the initial guess based on CT. It was during contrast injection, requiring the three cusps to be in a single plane for Edwards. For the core valve cases, a more LAO projection is required, and a second correction is made so that the radiopaque marker at the distal aspects of the valve was co-aligned. To measure the post-deployment angle, this was done after the TAVI procedure, and initially we take by fluoroscopy, we find initially the projection might not be exactly coaxial, but by adjusting the angle, we eventually find a plane where the prosthesis is orthogonal to the fluoroscopic projection. And this we can see where there's overlap of struts. Here we can see there's no overlap of the anterior and posterior aspect, whereas here it is, so we know that we're orthogonal to the valve. To calculate the difference between the predicted and post-deployment angles, we did the following. We took the location that was actually used during the procedure, we plotted that on the plot of the line of perpendicularity, and we measured the distance, the closest difference to the line of perpendicularity, which can be represented as the LAO and craniocaudal coordinates, and as the sum of those, well, not the sum, but the distance from this point to the curve. So we actually have three numbers, LAO, RAO, and an absolute difference. Our results, in comparing between predicted and post-deployment angles, firstly, the post-deployment angles on average were LAO 17 and caudal 2. The closest point on the line of perpendicularity averaged LAO 13 and cranial 2, which means there's an average difference of 4 degrees in LAO direction and 4 degrees craniocaudal direction, with the perpendicular distance being approximately 9 degrees. If we now look at the difference between automatic and manual methods, we see the automatic method, the average distance is 9 degrees. For the two manual operators, it's also 9 degrees, so there's no difference between automatic and manual methods. If we just compare operators, don't compare to the deployment angle, we find the difference between operators is about 3 degrees, average is 3 degrees, and the difference between the operators and the automatic is also 3-4 degrees. So there's no difference between automatic and manual methods for assessing the line of perpendicularity. Now when we compared Sapiens and core valve, interestingly there was a large difference between the two, where the Sapiens seems to be much closer than the core valve. And when we analyzed this more in a more deeply, we found the following. Firstly, for Edwards, if we look here, this is LAO and this is cranial. The initial angle, the predicted angle was average 12 LAO, 1 caudal, and the actual post-deployment was 13.2. In other words, there's no difference between the two, so it gives you a correct assessment. For the core valve, on the other hand, the predicted was 13 and 5 cranial. The actual closest point, this was the closest point. The actual post-deployment was 21 LAO and 3 caudal, with a difference of 4 degrees LAO and 4 degrees caudal. In other words, there's a consistent bias of 4 degrees LAO and 4 degrees caudal compared to what would one expect. So we try to think what could cause this difference, and perhaps this is our hypothesis. If we look here, this is what happens before this is an example of a core valve implantation. Before deployment, we see that this is the annulus, this is the sheath, which seems to be pretty coaxial. Here at the beginning of deployment, it's still okay, but what happens afterwards, we see this angle performs. And why do we think this is happening? We think it's because the valve actually enters the aorta itself, which is curved, and we have the greater and lesser curvature. The part of the greater curvature is going to be shortened relative to the lesser curvature, which could possibly account for that difference. Here's another example, which is simply easy to see. This is not from the study, but this is a case where we had a bioprosthesis valve in valve, and it's just easy to see the annulus of the valve, initial valve and the core valve, where once again we see that same displacement. Time to complete analysis. the fully automatic took 19 seconds, the manual method took 2 minutes, the semi-automatic, in other words, with corrections, took 73 seconds, so there's this time saving of 98 seconds for the automatic method and 43 seconds for the semi-automatic method. And I'll conclude with the following. Fully automatic evaluation of pre-procedural CT images for TAVI planning accurately calculates the optimal deployment angle. There were significant differences between Sapiens and core valve, the latter being consistently more caudal than LAO, and this perhaps needs to be taken into account. Although additional manual corrections required to achieve accurate annular dimensions, didn't actually do this, but I'm going to say it anyway, significant time saving still is achieved in comparison to manual evaluation. The automated approach will likely result in less operator dependence for TAVI planning and higher accuracy in deployment, and this potentially may enable less experienced readers to achieve better results. Thank you.